Okay, so welcome to the second session of PriSC. The first speaker is Matteo Busi, and he will tell us more about automated learning and verification of embedded security architectures.
Okay, thank you, Kathleen. I'll start a timer so I won't go too long. So today, I'm currently a postdoc at the Focardi University of Venice, and I'm working with Riccardo, Focardi, and Flaminia Luccio on these automated learning things. And I will start my talk with a rather philosophical question. What's a typical approach of us people working in formal methods? Well, it's called the deductive approach. You typically have your system. Well, we do security, so we have an attacker, and the attacker interacts with the system. And once you choose the system, you identify how it's running against the attacker, then you do the formal work. You model the system like these boxes here, their interaction, and then you try to prove something. But you actually prove something not about the system, but about the model. And this is fine. We are happy with that most of the time. However, you may have heard of the quote that all models are wrong. So for instance, this is well known, like everybody that works in formal methods knows this, but there is a nice example by Bognar, Van Bulk, and Pistons on some TE's implementations, for instance, Sancus and Erased, that have the characteristics of having both a real-world implementation written in Verilog that runs programs, etc., and a corresponding formal model that tries to capture what the implementation do. And the nice thing that, well, the bad thing probably that they highlighted is that the formal model have different security guarantees with respect to the actual implementation. And in particular, they discovered that some attacks are not modeled in the formal model, but they are there in the implementation. And this is, of course, a problem because this gap is important if you are interested in this kind of stuff. And in particular, well, it was interesting for us because we were asking the question, okay, can we do something about this? Can we identify this gap and maybe make it smaller or at least bridge it in some way? And the answer is that, well, classical experimental sciences do that in some sense. So they use what's called the inductive approach, which is typical, for instance, for attack research. And what they do is actually take a system, take the attacker, which is in the form of some text and experiments you do on the system, and, well, observe the system's behavior interacting with the attacker and try to conclude something like, well, this is an attack, this is a bug, this is okay, but we need to fix it, etc. So, as a formal person, I was saying, okay, this is nice. Can we have a more formal look at this? And the answer, at least for us, since we were interested in security architectures, and in particular on leakage model of security architectures, was okay. We are actually testing something which is some variant of robust non-interference. Well, non-interference, robust means that it holds against all the possible attackers you can have in mind. And, well, a bit more formally, we were inspired by previous Riccardo work on process algebra, and we were like, okay, we can look at the behavior of a victim when interacting with an attacker A drawn from some family of attackers on a system S. And we were comparing the behavior using this relation here, which is induced over this O, which is the set of interesting observables, so which are the interesting behaviors of your system. And this comparison was done against the running of the victim in isolation on the system S. Of course, this is not very formal, since I'm not saying what this means for V to run in isolation, but it's just to get you the intuition. However, if you think about how we usually develop systems and this kind of architectures like Sancus, you may discover that non-interference is not enough. Since assumptions break over time, system evolve, the system evolves, attackers change, we discover new stuff about attackers, etc. So what shall we do then? Well, maybe we can take inspiration from secure compilation. And actually, what we thought was, well, we can take the preservation of robust non-interference, which is PRN, which we call, I don't think it's called in general, but we call PRNI. And what does that mean? It means that if you have your good old non-interference here, you rewrite it, but on a different family of attackers and on a different system. And then what you want is to preserve it. So you just want this implication. This arrow here is an implication, but you can think of it as an arrow of time. So as time passes, your attacker evolves, your system evolves, and you want to preserve this no interference. Okay, this is nice. This is also simple, but we came up with two different interesting scenarios, which are, as I was telling you, the scenario in which the attacker capability evolves over time. So we fix S and we change the attacker capabilities, and we call it PRNIAC. And the second one, you fix the attacker, you change S. So S blue and S red are two different systems, or maybe two different versions of the same system. And then you get these security regressions to get the idea that you may be changing the architecture, or changing how you define your ISA changes the security guarantees of the system. And okay, so the next question is, okay, this is a nice way of seeing it. Can we do something a bit more practical? And the answer is, well, we could follow two different approaches. We could follow a top-down approach, which is actually what has been done before. So you take a specification written in semi-level language, you define a compiler, you compile down to, I don't know, Verilog, for instance, and you get all the nice guarantees. Very strong, very powerful, but it's not always possible. If you have an existing system that you don't know how it works, you cannot apply this. The other alternative, which is the one we followed, is the bottom-up approach. So you try to extract the models of the model of the system automatically, and this is actually has been done in the past. Actually, it was also very successful. And then you try to model, or well, to prove something about the model. And well, you have nice things which are, okay, this is a gray box approach or a black box approach, so you shouldn't, well, you don't need to know a lot about the system. But scaling may be still hard. So for instance, we cannot hope to do automata, well, this bottom-up approach, which we'll call automata learning, we cannot do that on x86, for instance, to learn the whole model of x86. And also, this is still an abstraction, so you must be careful because you may lose something that is of interest for you. Okay, so we chose to go with this second bottom-up approach. Let's go ahead and see how we actually do it. So we do the bottom-up approach via automata learning, and automata learning has this fancy name that reminds you about machine learning, but it's a bit different. And well, automata learning allows you to derive, well, what's an under-approximated model of a system in an automatic fashion. So you get your system that interacts with some attacker. You get some, let's say, a lens to look for it, and you have a teacher that answers two kinds of questions. The first question is the output question. So you provide the teacher an input I, and the teacher tells you what's the output of this whole interaction here when given the input I. So for instance, if I give the system an add instruction, the output will be, okay, add between 2 and 3, the answer is 5. And the second thing is this equiv query. The equiv query is a bit magical, since in the original paper by Anglin, it was like an oracle. So you give it a model, well, an hypothesis of what could be the model underlying the system that you don't know, and it replies to you whether your hypothesis is correct, so it is equivalent to the system, or otherwise, it provides you a counterexample of showing you why the system is not equal to the model. And of course, all of you know that this is a very hard problem, so this is usually approximated in some way, so that's why I put under-approximated here between parentheses. And okay, so we have this setup here, and how do we learn something? Well, we are the learner. We have a strategy to ask these two questions in a particular order, and we try to derive a formal model of the system. And the model for us is, we are interested in actual hardware implementations. It's a mini machine. So very roughly, a DFA with I/O on the edges. Okay, so hopefully this wasn't too badly explained. So we can go forward and see how we can combine automata learning and PRNI. And in particular, we take this thing here. This is the implication we had before. And well, we do automata learning on the premise, we do automata learning on the target, on the consequence, and we get this model here that you see on the top, which is the blue attacker, well, the family of blue attackers interacting with the family of victim programs, and this is a model. This is the model of the victim running in isolation, and the same for the red thing. Actually, this one here and this one here are the same. So you get the idea. We just check if this implication holds, and we can do that because these are like milli machines, and everything is rather easy on milli machines, right? So let's see how we did that on an actual security architecture. And for that, I will stick to an example, which is this PRNA IAC, in which, again, we have the same system, but different attackers. So how we did that? Well, we first needed to define which is the family of interesting victims and attackers in our world. So for that, we defined a DSL, which is very simple, and which we applied actually, only to the Sancus architecture, in which you have the victims that you are interested in knowing their security properties that are some enclaves, and the attackers that model everything else. So our DSL for the victim is rather simple. You have this enclave section, and then you have a body, which is very roughly a regular expression, where you have choice, you have sequencing, etc., and then you have standard addition, jumping, and so on. So this enclave, for instance, is a singleton family of enclaves, actually, and does an if-then-else, checks if R5 equals to some Boolean pass, and then increments the counter and exits. Otherwise, it simply exits and does nothing. This is it. And then we need to specify the family of the blue attackers and the red attackers. And well, the blue attacker is this way. So we have a cleanup section which is empty. The cleanup section, you can imagine it as the last piece of code that runs before the processor turns off. And the ESR section is the piece of code that runs when an interrupt arrives. And for our simple example, this is just empty. And this prepare section, this is actually the setup phase that runs before running the enclave, simply create an enclave and jumps inside of it. This is very simple again, but this is an example. And what about the red attacker, the one on the right? Well, the red attacker has an additional capability. For instance, during time, we discovered that it can also set register R5 either to 1 or to 0. Very simple. And actually, this defines a family of attackers, which is of a family of two attackers, the one that sets R5 to 1 and the one that sets R5 to 0. So let's see that in action. Let's learn something. And well, the learning phase, I won't go over the details, but it's obvious for you to know that when we learn the behavior of the victim alone or inside of the blue attacker, we get this simple model here. We start from the state 0, we create the enclave, which is a silent operation. we jump inside the enclave, and then we perform this UBR, which is just a shorthand for all the if then else that we had in the specification, and this takes 12 cycles. In the red attacker, in the red case, the things are a bit more complicated. So we have this create enclave. We either set R5 to 0 or R5 to 1. Then we jump into the enclave, and you can see, since this enclave is kind of a stupid enclave that behaves differently depending on the value of a secret, it either takes 12 cycles or 6 cycles. And this is, of course, something that we would like to catch, right? So we move to the verification phase, in which we actually check for something which is similar to a bisimulation between the model of the victim running in isolation and the victim running against the red attacker. And what we discover is that, well, there's a counterexample. This is what we call a witness graph that witnesses all the counterexamples for the weak bisimulation that we are checking. And in particular, you can see that we create the enclave. On the empty attacker, well, on the victim in isolation, this corresponds to doing nothing. Then we jump inside the enclave, and in the empty attacker, the enclave takes 12 cycles. Instead, when you have the red attacker, you, like in the case in which you set R5 to 1, that's fine. If you set R5 to 1, you jump inside the enclave, and then this takes 6 cycles. So this is a violation. There is a difference between these two, and we highlight that. Yeah. So, going to some more realistic stuff, because this was a toy. The leakage model was pretty simple. What we did was to move on the full Sancus, and we had one big specification for enclaves, which is something like, okay, your enclave can do more or less any assembly operation that you can imagine in whatever order you like. Well, it's a bit more restricted than this, but just because of to keep learning times low. Then we specified attackers, and for that we classified the attackers proposed by Bognar, Van Bulk, and Pissens to the capabilities that these attackers have, and we run the learning changing these capabilities and comparing different attackers with different capabilities. So, for instance, examples of capabilities are manipulating protected memory, which shouldn't be a thing, but apparently in the implementation it was possible nonetheless. Capability to observe the execution time of the instructions, ability to jump in the middle of an enclave, which is usually forbidden, and stuff like that. In total, we had 10 attacker specifications plus, 4 extra tests that we run on the models. We run extra tests on the model just by hand using our simulator, but this is another thing. Okay, so with this setup, what we did was to try to reproduce the attacks that were discovered by Bognar and Van Bulk and Pissens. And what we discovered is nice, in the sense that we were able to rediscover all the things without looking at the code, just looking at the models, except for, you can see here they have these kind of attacks going from B1 to B7. We have B1, B2 is not there because it's about it was a bit end wavy to do with this specific setup, I will be honest. We have B3, B4, B6, and B7. B5 is missing because it's about a reentrancy problem when you have 2 enclaves, which we don't deal with yet. And the nice thing is that we were able to find these bugs on the original commit, on the bugged version of the system. But if we took the model of the patched version of the system and also of the patched version of the patched version of the system and also of the latest version of the system, the model reflects the fact that these bugs are fixed. So this is nice. And that's more or less it. Concluding, what we proposed is like a principled way of doing testing in some sense, and we applied it to a specific architecture, real-world architecture albeit simple, which is Sanku's TE. And what we were able to do is to learn a mealy automaton and reproduce the known issues on it. So this is nice. And in the future, well, we are currently working to make our tool more modular and maybe just be able to capture more naturally the bit2 attacker and the bit5 attacker. And what we're actually trying to do is also to automatically build regression tests. Since when you have the witness graph that we had before, like with all the counterexamples, you can just collect them and keep them like in a database where each time you have a new version of your system, you check for them all without redoing the learning, which is somewhat costly. In the future, we would like to be more customizable, maybe using richer models that can deal with data, for instance, and maybe different properties. And that's it. Thank you for listening. I'm happy to take any question.
Thank you, Matteo. We have time for questions.
Thank you, Matteo. So as input, as data, as arguments to your algorithm, I suppose you have to give a concrete enclave, right?
Yeah, because well, I didn't tell you, but this DSL gets compiled to concrete code.
Okay. So it has to be pretty slow to test against every enclave, right?
Yeah, it is. That's why we use automata learning, because doing like a lot of tests, like 1 million tests, takes a lot. So automata learning is a bit more efficient, is a nice way of doing testing. So what we do, actually, we pre-compile this to some code. We pre-compile the Verilog code using Verilator, which is fast.
Let me make the question first, and then you can continue. I was wondering if you could just supply an abstract enclave and do things symbolically. That's my question.
You could, but I mean, you'd need the semantics, right, for the enclave. And that's, again, the problem we had with Sanku's model, with our original Sanku's model, which is like too distant from the implementation.
Okay.
So
right.
So I've got a question about that. It seemed like there was a bit of a jump between the introduction to this talk, where you're talking about like all models are wrong, which is perfectly fine position to take. But then the experimental setup that you had for your learning algorithm, it could answer 2 questions. And one of them I can see that you can actually do with the system under test.
Sorry, I didn't get the last.
I'm just like, okay, you feed an input, it tells you what the output is. Yes, you can do that with just a black box system. But the second one is you can query the oracle and say, well, I think this is the model, and this is essentially the kind of directed randomized testing setup where it will come back, well, either saying yes or it will give you a counterexample. And that part, normally you need symbolic execution for. So I don't quite understand how you could to line that up with the setup.
Yeah, it's actually, we don't do symbolic execution. What we do is actually, well, it's rather standard to do that in automata learning. And what we do is to have the mealy automaton on one side, our hypothesis mealy automaton, and we randomly visit that for some path, and we see if, for some state, there exists some input for which this input is, the other way around. We generate some code, some abstract code from this model, from this specification here. We visit we run it on the actual system, and we compare this execution, the trace of execution of this on the system against what's the hypothesis on the model. So we run that concretely.
Okay, so it's just randomized testing rather than...
yeah, it's more or less randomized testing, yeah. It's there, actually, it's directed by this specification here and the model.
Okay, so probably last question.
Okay, so super cool. So we did some work at some point on using automata learning and testing for timing properties. And one of the things that, in my experience, really helps is, you know, it's not just learning a model. You want to learn a model that is useful, right? And I was wondering, do you have some ways of like constraining the complexity of the model that you're learning and explaining it to the user?
Okay.
I mean, okay, here it can be simple. I'm just imagining, I mean, if you want to learn some part of the microarchitectural behavior of a processor,
Okay.
good luck, you get like it.
Okay, yeah.
Well, automata is incomprehensible.
Okay, yeah. Well, one thing is that we don't actually want to learn the whole microarchitecture. Yeah.
Next steps.
Oh yeah, sure. The point is that we tame the complexity of like exploring the whole possible programs and attackers in this in the world of Sancus. We did that by providing this specification. So using this specification, the learning actually doesn't try the usual stuff like for any possible input, but it actually generates code that is just, well, not completely, but just in this specification here. So you just explore that subpart of the system. And I don't know if this helps, but I think this is the way to keeping the model manageable and understandable. Of course, we don't have a way like the real model for like these attacks here. I think for B1 with the correct attacker, etc., has something like 1,000 states or something like that, which is hard to follow, right? I mean, I open it up and I don't know what to do with that, but the model checker can do. So.
I mean, if you want to learn real systems.
Yeah, it's small. Yeah.
Okay, so we need to move on to the next talk. Let's thank Matteo again.